All right. Good morning, everyone. Again, my name is Maria. I'm a grad student at UC Merced in the heart of California. And today I'll be talking about using strong gravitational lensing as a probe for dark matter, and in particularly focusing on the light source. So let's start us off with a little bit of background. So different models exist trying to understand what this mysterious dark matter particle is. And some of the distinguishing properties between these models is the number density and profile of these dark matter halos. And dark matter halos are these self-gravitating dark matter structures that we believe are formed in which galaxies reside. And so here I have the distinguishing two models, cold dark matter versus warm dark matter. And we can visually see in this simulation how many small mass dark matter halos are, which are the little dots that you can see there. We can also visualize it in terms of the halo mass function, which is on the left here. As we can see, warm dark matter predicts a lot more of these low mass dark matter halos with this turnover in the halo mass function. And so placing constraints on this halo mass function allows us to then place constraints on the kind of particle physics that dark matter predicts. And the method that we use is gravitational lensing to test between these models. And so gravitational lensing, to remind us, is when light from a distant light source gets bent by the mass of some foreground galaxy. And in particular, the flux ratios, or how bright these images are used as probes to test for dark matter. And I can talk about that flux ratio anomaly method. So here I have an example of a simulated lens observation. This is what us, the observer, would see of this quadruply lensed quasars. And again, this is just a simulation with one main galaxy doing all the lensing. Now we can compare that with the simulation when we place one dark matter halo near one of those images. And if we take a look at the difference between those two images, we can see that there's some flux anomaly, right? Meaning that the image is a lot brighter when you have the dark matter halo. Now, in reality, we don't just place one dark matter halo in our simulations, but rather we create realistic populations of dark matter, and we perform statistical inference to see how likely is it for one specific population to explain our observations. Now, using this flux ratio anomaly method, there's been some great work trying to place constraints on the warm dark matter, or this turnover, the half mode mass. And so I can mention a few of those here, but I won't get into detail about that. And a lot of these is using the narrow line region. So this is where I'll transition into the light source and my particular work in this overall dark matter story. So the narrow line region is this low density gas area of the quasar. And the important thing about the narrow line region is that it emits, because it's low density, it has these forbidden transition lines, which in particular the O3. Now, the narrow line region is of particular interest because it is sensitive to small scale perturbations, meaning if we were to see, or if we were to have any dark matter halos, we would be able to detect them, but also it remains large enough to avoid any microlensing by stars. So any kind of other signal that might happen from, stars also have mass, so they might have some microlensing effects. The other exciting thing is that we can measure these narrow line region flux ratios in some of the upcoming missions. So the hope is that we'll discover many, many more lenses with these missions, and the narrow line region will really be the workforce for these observations. Now, in terms of using Keck, and Keck can allow us to detect or observe these gravitational lenses, taking advantage of the adaptive optics at OSIRIS, as well as making sure that we have IFU data, because we really want to make sure that we're using the light from the narrow line region. So we really are looking for that O3 emission line. That's what we use Keck. And so understanding the observations is kind of like putting different puzzle pieces together. We have the source shape and size, which is what I focus on. We have a lot of people working on the mass of the lensing galaxy. So what does that look like? As well as, having a good understanding of the observational component, like the sky noise and the PSF. So the previous model that we've used to describe the narrow line region has been a Gaussian, which has worked really well for most of the lenses that we've observed so far. However, there's a few new lenses, one of them 1413, for which there's a simple model. As you can see here, we have the continuum versus the O3 white light images. And so we can see that there is some extra extended narrow line emission. In this case, this previous model, the Gaussian, is not a good enough description. So that's sad face. And so we can also try to look a little bit deeper, and we understand that narrowline regions actually are a lot more complex, right? We have some extra elongated features or some clumpiness. So really, maybe a Gaussian might not be the best model, but maybe we can start exploring a little bit more added complexity or just creating a more flexible model. And that's what my work has been doing in developing a more flexible model that allows us to then fit these new lenses for which we see this extended emission. And now I'll give a brief overview of kind of the work that I've been doing. So I've created two main pipelines, one to simulate lenses and then another one to then analyze these lenses. So first I start with real sources. So these are real narrowline images, and then I can perform some lensing calculations and generate these mock Osiris lenses. And all of this is done using Lenstronomy, which is open source gravitational lensing software. Now I can then pretend that I have these observations. So this is if I were to actually observe with Osiris. In this case, I'm using my mock lenses as my observation, of course, to test my pipeline. And then I can then estimate the lensing parameters. And in this case, instead of assuming a Gaussian light source, now I'm introducing a new model for which I've been using a Sursich profile, a Sursich ellipse. And then from there, I can then calculate the flux ratios and see how well is my new pipeline recovering those flux ratios compared to the model. Now, for the light sources that I've been using, these are some of the brightest nearby quasars that I've been able to find, for which we have really good spectral data, right? So these are 5 sources that I've used here. And a lot of these have a bolometric, the sample that I'm using has a bolometric luminosity of about 10 to the 46 ergs per second. So these are, again, some of the brightest things that I could find. Our typical quasars have luminosities that are similar to this, if not even brighter. So finding really bright things nearby is kind of hard. And now talking about how I create the lenses, I create a multiple component lens. So I have 2 main components. One is the lensed O3 region. So this is, I'm using the O3 maps that I showed you earlier for the source, and I'm just lensing those as is. And then they have their own simulated O3 spectrum. So then I have my double peak right there, and that's my narrowline emission. Now, for the rest of the emission line, because the quasar also has emissions from other components, right? It's not just narrowline region. That would make our lives so much easier. But the different sources are then unresolved, and I simulate them as if they were coming from a point source. And then they have also their own respective spectral signature as well. Now, I can add those 2 things together, and then what I'm creating is, of course, a cube, right? And then I can add some realistic sky nodes from a typical Osiris observation, and I can have my final joint spectrum or joint image. That is the simulation component of it. Now I can work on fitting these observations by taking a wavelength range over that extended or over that O3 region for which I expect to see this extended emission. And this is, for one of the lenses, is this 3C273. And now I can fit that white light image using, for the lens, I'm assuming an SIE plus shear. And now again, for my source, this is why I introduce the flexibility of my new model, which I'm assuming is Sursich ellipse. And you can see I can recover them very well, which is really exciting. And then the next thing is I don't just want to fit over that wavelength region, but I want to then have those best amplitude components and perform a linear inversion so that I can get the recovered spectra over the whole wavelength cube. And so this is the recovered spectra for the point sources. So each of those point sources has its own respective spectra, and I'm able to recover them very well. So it might be a little hard to see, but the input is in blue. So that's my input spectrum, my simulated input spectra. And then the recovered spectra is what my model then spits out. So I do a really good job at recovering that as well. Now I can do the same. This is an example that I've shown you for just one of the lenses, right, to kind of visualize it, but I can do it for all of the 5 sources that I have, and then kind of see how well am I able to recover those flux ratios that I was talking about. So this flux ratios, again, is what I need in order to do the dark matter analysis. So this is what is important for us to see whether or not we can place better constraints on the dark matter. And for the 5 sources, I see that I do a really, really good job at recovering them, actually, because the typical flux uncertainty is about 6%. So all of my measurements that I have fall well within that uncertainty measurement. And this is just plotting them, those 5 sources, as a function of the Sursich radius and the Sursich index for those sources. And then I can also, what I'm starting to explore is the different lens configurations also affect this measurement as well. So here I have an example of the three different lensing configurations. And for most of these, I've been working on it with the cross configuration, but I can also explore what it looks like for a cusp and a fold. And I can still see that I'm well within the typical uncertainty measurement, which is really exciting. So all it is to say is that I'll just kind of talk about my summary here is, I've created this awesome pipeline that allows us to generate realistic or lenses using real narrowline regions, analyze them, and we see that actually the extended emission doesn't affect as much as we hope, which is a really exciting thing because that means that even if we do see it, we're able to now, with my pipeline, manage, be able to fit it, but also it doesn't end up affecting the flux ratios that we measured. So yeah, with that, I can take any questions. Thank you.